Hello juniors, today we're going to see electronic assignment 15, which is about the binomial distribution. Today we're going to start learning about a new tool that will help us or facilitate us to calculate probabilities that are widely used in real life situations. Okay, so two objectives for today's class. The first, define a binomial distribution, and number two, apply binomial distribution to solve problems. So first of all, what is a binomial distribution? It says it's a type of frequency distribution used when there are exactly two outcomes from each trial, and those two outcomes are either a success or a failure. We're going to see this through examples in a second. So then it says the essential elements of a binomial distribution are: number one, there's a fixed number n of trials. Number two, each trial has only two possible outcomes, either a success or a failure. Then the probability of a success, P, is constant from trial to trial. That means that it does not change from one trial to another trial. And finally, trials are independent of each other. This is very important. In order to be able to apply binomial distribution, we need to be talking about independent events, okay? So then it says, the outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called binomial distribution. Here you can figure out why the name binomial, right? Bi comes from two. And why two? Because we talk about trials in which the outcomes are only two, success or failure. Okay, that's why we talk about binomial distribution. Then it says, the binomial distribution describes the behavior of a discrete variable x if the conditions above apply. Then, the parameters that define a unique binomial distribution are the values of n, which represent the number of trials, P, which represents the probability of a success. So any binomial distribution is represented as, and this is the symbology to represent a binomial distribution. This means that the variable x can be modeled through a binomial distribution which has n trials and the probability of success is equal to P. Okay, so that's how we interpret or how we read this symbology over here. So let's see an example in order to be able to visualize what this is about. It says, example, consider a biased coin where the probability of obtaining a head is 2/3. Obviously, that means that the probability of obtaining a tail would be 1/3, right? So, what is the probability of obtaining exactly two heads in three tosses? We already know how to calculate this, right? We would say that the probability of two heads in three tosses, we can have different alternatives in our universe. We can first, for example, get head, head, tails. Then another alternative would be head, tails, head. And finally, the last alternative in the universe is tail, head, head, right? If we calculate the probability of each of these, we're going to say that, for example, head, head, tail, remember that the probability of head is 2/3, right? So head, head, tail is 2/3 times 2/3 times 1/3. Then head, tail, head would be 2/3, 1/3, 2/3. And finally, tail, head, head is 1/3 times 2/3 times 2/3. So if we organize these terms, we're going to see that this is 2/3 squared times 1/3. Then again, this is 2/3 squared times 1/3. And finally, this again is 2/3 squared times 1/3. So we see that we have the same expression written three times. So we can write this in a more summarized way and just say that it's three times and the probability of one of them, which is 2/3 squared times 1/3. And this would be the probability of obtaining two heads in three tosses for this particular case, right? Where we have a biased coin. So it's 4/9. So remember this, because here we have some important elements that we're gonna later generalize into a formula, right? So then for part B, it says, what is the probability of obtaining exactly two heads, but now in 6 tosses? So here's where it gets a little bit more complicated. You see that for this case, it was easy because we just did 3 tosses. So making the tree diagram in order to be able to see all of the different alternatives is easy, right? Or if we enumerate all of the different alternatives, for example, head, head, tail, or head, tail, head, and tail, head, head, is easy, right? When we have 3 tosses. But what about when we have 6 tosses? This becomes much more difficult because we have lots or many more options than for having only 3 tosses. Or what about if we had 100 tosses? There will be thousands, maybe millions, not millions, but thousands of alternatives, right? So there needs to be a way we can generalize this, or a number we can a way we can find this number of combinations more easily, right, than actually doing or listing all of the elements. And we're going to see this in a while. It says, so what is the probability of obtaining exactly 2 heads in 6 tosses? Before we answer the question, it says, first note that the conditions for a binomial distribution have been met. The first condition was that there's a fixed number n of trials, and in this case there are 6 trials, right? We have 6 tosses. So we can say that the value of n is equal to 6. Then each trial has 2 possible outcomes, either a success or a failure, and it is true. Here a success is getting a head and a failure is getting a tail. So that's fine. Then the third condition, the probability of a success p is constant from trial to trial. That's true. The probability of a success is 2/3 each time the coin is tossed, right? We have a constant probability of obtaining head in this case. Here the value of p, the probability is 2/3. 2/3. And finally it says trials are independent of each other, and that's true also for this case. Getting ahead on one trial will not affect the outcome of the next trial. So all of the 4 conditions in order to obtain a binomial distribution are met. So we are talking about a binomial distribution problem, right? So it says one combination of heads and tails that will produce 2 heads and 4 tails, which is what we're looking for in this problem, 2 heads in 6 tosses, is head, head, tail, 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 right? And the probability for calculating this, head, head, tail, 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 is, we have seen this already, it's 2/3. The probability of head, it is repeated twice, so squared, times the probability of tails, which is 1/3, and this is to the 4th power, right? Because it's repeated 4 times. So if we calculate this, we're going to get this value for the probability, but this is only one of the alternatives if we throw the die 6 times and obtain 2 heads, right? So then it says, and every possible combination of 2 heads and 4 tails will have the same probability, right? So we need to determine how many combinations are there if we throw a coin 6 times, right? And obtain only 2 heads. So, but how many combinations are there? So this is the way in which we can calculate how many combinations we have. It says n trials taken r at a time, that's how we read this, represents the number of ways of choosing r items out of n items. And here we have the different ways for calculating. It says the number of combinations of 6 items that have 2 heads and 4 tails is therefore n, which is 6, and the value of r is 2. The value of r is the value we want in this case. In this case, what we want is obtaining 2 heads. Or if we want to look it from another way, if we can call n, number of trials is 6, but the number of times I can obtain tails would be 4, right? So actually writing this and writing this produces the same result, and the result is 15, okay? So 15 is the number of combinations I can find for getting only 2 heads in 6 tosses of a coin, right? So this is a value that is very important to calculate a binomial distribution. Okay, so how do we calculate this number? Because we just saw this symbol, but we don't know how to calculate this. Okay, here are 3 ways in which you can calculate this. One way is to use your graphic display calculator, and where you're going to put this in your calculator and you're going to click on execute, and you should get the result. I want to show you this in the calculator, just a second. So if you see my calculator right now, in order to do this, to find the combination of 6 trials taken 2 at a time, we're going to go to the menu 1, right? The principal menu. We're going to delete this. And you're going to click on option, and then you need to search for the option that says prob. We don't see it here, so we're going to click on the arrow, which is F6. And here you have prob, which is F3, right? You click on prob, and here you have NCR, the letter C represents combinations. The letter P represents permutations, but we're not using this for for our RAB program. We're only using combinations. So you're going to click on this, which is F3, right? F3. And there you have the C. And to the left side, you're going to put the number of trials, which is 6. And to the right side, you're going to put the value of R, which in this case is 2, right? We only want to get 2 heads. So you click on 2, and then you click on execute, enter, and there you get the value of 15. And if you see, let me put this again, but instead of writing, I'm going to erase this, instead of writing 2 to the right side, I'm going to write 4 to represent the number of tails. And you'll see that we're getting exactly the same value, right? So it's the same thing if you click on, if you put 2 or if you put 4. The number of combinations is the same. Okay, so if we go back to the assignment, that's one way of calculating using calculator. Here you have the instructions to do so. Then another way of calculating is, instead you could use a formula. There's a formula, and this formula is available in the formula booklet, which is this one over here. It says the combination of n trials taken r at a time is calculated this way. It's n factorial divided by r factorial times n minus r factorial. And here you should know what factorial means. I think we have already seen this. For example, if we say 4 factorial. 4 factorial is 4 times 3 times 2 times 1, okay? Or, I don't know, 3 factorial. 3 factorial is 3 times 2 times 1, and so on, okay? It's the product of all of the numbers from this number and below, until 1, okay? So that's the concept of factorial. So in case you're not allowed to use calculator, you should know what factorial means. This is all in the formula booklet. Let me show you. If we go to a formula booklet, and we need to go to, this is topic 1, number and algebra. If you scroll down, you see binomial theorem here. And here you have the formula for combination, right? NCR is equal to n factorial divided by r factorial times n minus r factorial. Okay, so that's something that you should know how to apply in case you're not allowed to use calculator. So for example, you see that 6, 2, what we just did in the calculator, if we apply the formula, according to the formula, it would be 6 factorial, right, n factorial, divided by r factorial, which is 2, times n minus r. N minus r is 6 minus 2, which is 4, so times 4 factorial. So 6 factorial, let me do this here, for you to understand where this comes from. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, right? And this is being divided by 2 factorial and by 4 factorial. So 2 factorial is 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. So you see that all of these terms, all of this cancels out with all of this. So we're only left with 6 times 5 divided by 2. 2 times 1 is 2, right? So it's 6 times 5 divided by 2, which is exactly what we have here. 6 times 5 is 30. 30 divided by 2 is 15. So that's why we get as a result 15, which is exactly the same result we got using our calculators, right? Okay, so that's another way of calculating combinations. In case you're not allowed to use calculator, you have this manual way, which is applying a formula. And finally, there's a third way, which is using the Pascal's triangle. And here you will learn what the Pascal triangle is about. The Pascal triangle is a very important triangle in math in general, which has lots of properties. And building the Pascal triangle is actually pretty easy and fun at the same time. I'm going to show you what the Pascal triangle is about. If we put, for example, a 1, it always starts with a 1 right here. The Pascal triangle, let me write here, row 0, row 1, row 2, row 3, and so on. Okay, so the Pascal triangle is a triangle in which all of the edges of the triangle are always equal to 1. Well, the principle is that for every value that we have in the Pascal triangle, every value is composed of the addition of the numbers that are on top, right? For example, this one over here is 1 plus 0. We have a 0 here. If there's nothing, we have a 0. So that's where the 1 comes from, okay? So if we do the other edge of the triangle, we will also have a 1 over here because it's 1 plus 0 and so on. And all of the edges would, by consequence, will always be 1, right? Because it's always 1 plus 0, 1 plus 0, and so on. But what happens with the values in the middle? For example, what value should we put here? The value we should put there is 1 plus 1, and 1 plus 1 is equal to 2, right? So this is 2. Then, for example, here we're going to put 3, right? 1 plus 2 gives us 3. And here, 2 plus 1 is also equal to 3, right? And we can keep on doing the Pascal triangle. For example, if we go to row number 6, this keeps on being 1, 1, and 1. Here we have the same thing, 1, 1, 1. Then this element over here would be 4. Then this is 6, right? 3 plus 3, then 4 again here. Then we're having, this is 5, this is 10, 10 again, 5. And finally, for the 6th row, this is 6, 15, 20, 15, and 6, right? So we have built our Pascal triangle up to the 6th row. Obviously, you can continue this. I remember when I was in school and I studied Pascal's triangle, I made all of my cover pages for all my different subjects by completing all of the grid paper with a huge Pascal triangle. And it is something that is fun to do. So if you pay attention, what we're looking for, remember our objective is to find the value of 6, 2, right? The combination of 6 trials taken by 2 at a time. So if we look at this mathematical notation and we associate it with the Pascal triangle, the 6 over here is the indicator of the row we need to look in the Pascal triangle, and the 2 over here is the indication of the position where we need to look at the Pascal triangle. Position. Okay? So, well, actually there's something you need to pay attention there. The first element here, we know that we need to go to row 6, right? So row 6 is all of this row over here, right? Row 6. But the first element is not actually position number 1. That's a common mistake students usually do. The first element is actually 6, 0, okay? We start at position 0. So then the second element would be 6, 1. And the third element, which is the one that we're looking for because it's 6, 2, is, well, let me finish this symbology first. This would be 6, 3, 6, 4, 6, 5, and 6, 6. We should always finish with the same number n, right? 6, 6 in this case. So you see that again, we're getting this value 15, which is exactly the value for the combination when we take 6 elements 2 at a time, right? So that's another way of calculating the value of the combination. Building the Pascal triangle up to, well, we need to look at up to this row, 6th row, and look at, in this case, it's actually the third position, right? It's the third element of the row because the first one is always 6 or n and 0, okay? So that's another way of calculating the binomial coefficient, okay? Later on, I'm gonna attach a YouTube video, which talks about the Pascal triangle for you to see because this triangle is pretty interesting and it has lots of properties that are normally used in our daily maths, right? Okay, so here's a 2K question for you to think about. It says, a model might not be a perfect fit for a real-life situation, and the results of any calculations will not necessarily give a completely accurate depiction. Does this make it any less useful? What do you think about that? Remember that math are always estimations of real life, or it's trying to model real life situations, but due to many reasons, they are not always 100% accurate, but they are useful in order to make predictions. Okay, so finally, it says, therefore, the probability of 2 heads in 6 tosses is given by this expression over here. the number of combinations that we have for 2 heads and 6 tosses, which we now know it's 15, this number over here, times 2 to the power, 2/3 to the second power, which is getting 2 heads, right? And 1/3 to a 4th power, which is getting 4 tails, sorry. So we multiply all of that and we get the final result, and this is the probability of obtaining 2 heads in 6 tosses, okay? Then it says, how can you tell if a real-life situation can be modeled using a binomial distribution? Okay, we already know that. In order to be able to determine that, these 4 conditions must be fulfilled, right? Super. Then here we have an International Mindness article, which is about the Galton board. I'm not going to read this because we're going to waste too much time, but I encourage you to read this. And maybe if you want to investigate, actually the video that I'm posting will be related to the Galton board. So if you want to watch that video, it's pretty interesting. It obviously talks about the binomial distribution as well. Okay, so finally, to generalize this method, or generalizing this method gives the binomial distribution function. And this is the most important thing about this class. This formula, where does it come from? Well, all of the investigation we just did was to generalize the formula, which we can apply for any type of binomial distribution. It says, if x is binomially distributed, and this is the symbology, this means that the variable x is binomially distributed with n trials and a probability of success of p, then the probability of obtaining r successes out of n independent trials, when p is the probability of success of each trial, is given by this formula, okay? Probability of success is equal to, the probability, I don't know what I did there. Here. So the probability is equal to the combination of n taken r at a time of the probability of success to the power of r times the probability of failing, which is 1 minus p, to the power of n minus r, or to the power of the remaining remaining alternative that I have. That's n minus r, okay? And remember, this nr is the same as saying this if we apply the formula, okay? This is often shortened to, and here you have a shortened formula, which is actually the same thing, but instead of writing 1 minus p, we write it as q, right? But q is calculated by doing 1 minus p, right? It's the probability of failure. If the probability of success is 2/3, then the probability of failure is 1 minus 2/3, which is 1/3. Just as we did in the example above, okay? And this formula is also available in the formula booklet. If you go here, we will scroll down, I think it's in probability, which is topic 4. Yes, topic 4. And no, there's no formula. It says binomial distribution. X has a binomial distribution, and the formula is missing, right? It's probability of x equals, probability of x is equal to, and here you have nr times p to the power of r times q to the power of n minus r. This would be the formula, which I don't know why, but it is not written here. Maybe it's written up here, topic 1, let me see. No, we just have this. That's weird. Okay. We don't have that in the formula booklet for now, but I think that's a mistake from the IB. We should be able to have this formula. Okay, but never mind. The idea is for you to understand what this formula is about. Where does it come from? Okay? So next class, I don't want to make this video too long. Next class, we're going to apply this concept of binomial distribution to to some examples for you to be able to see that this is actually not that difficult as it seems. It's pretty easy. And I'm also going to be showing you how to use calculator in order to make all of this process shorter, right? So whenever you're able to use calculator, I'm going to show you the steps you need to follow in order to be able to do so. Okay, so I hope this was clear. If not, please let me know. We're going to clear doubts in future live sessions. See you.